So if you remember that last week we were at this uh, example, which is about the modified secant method. So the method of modified secant method. So in the modified secant method, instead of taking the difference of two x values, you take a proportion of x value in the form of this delta, and then we multiply the initial value of the x with that delta, and then we follow the procedure. Okay, so now let's talk about another situation in finding the roots of the nonlinear equations, and that is the problem of the multiple roots. So multiple roots correspond to a point where a function is a tangent to the x-axis. And there are certain difficulties with the multiple roots. Function does not change sign at the multiple root, therefore cannot bracket the root. That means we cannot use the bracketing method. F prime of x, both fx and f prime of x are 0. So division by 0 with the Newton's and secant method. And then in that case, we also cannot apply Newton's and secant methods because there will be a division by 0. Okay, so let's look at these situations in the form of these figures. So in this first situation, you can see that at point 1, there is this curve, and then this curve touches the x-axis, but it does not crosses it, and then it remains on the same side of the y-axis. Okay, that means before 1 and after 1, the curve remains on the same side. So therefore, there is no change of sign in the function. So since there is no change of sign in the function, we cannot apply the bracketing method. And also at this point, you can see that the slope of the curve at point 1 is 0. So when the slope of the curve is 0, then that means the denominator used in the Newton-Raphson method is also 0. So when the denominator is 0, then we cannot apply that method as well. So in this case, this is a situation of a double root. It can be a it is just by looking at the graph, it is sometimes difficult whether to say that it is a double root or a triple root or a quadruple root or even any other type of root. But since we know that this is a double root, and then when we will plot it, so then we can say like this. But later on we will say that when it is a double root or the even numbered root or the odd numbered root. So in this case, since at point 1 it is a double root, and at point 3, of course, it is a crossing it. So this is a single root. In the next figure, here you can see that this is the example of a triple root. So in the case of a triple root, the curve will cross the point. Okay, the curve will cross the x-axis. Okay, so but in this case, what will happen is that since the curve is crossing the x-axis, you can see that while crossing the x-axis, the slope of the curve becomes equal to 0. Okay, the slope of the curve becomes equal to 0. So although in this case we can apply the bracketing method, but we cannot apply the Newton-Raphson method because the slope of the curve becomes 0. So for any triple root equation, then we will draw it, then it will cross the x-axis, and but the curve at the x-axis will be 0. And similarly for the quadruple root, it will be similar to the double root. Okay, it will be similar to the double root. So as in the double root, the curve will not cross the x-axis. In the case of the quadruple root, the curve will also not cross the x-axis. Okay, so in this case, then there are certain difficulties in determining the multiple roots. So none of the methods deal with multiple roots efficiently, because before, if there is a multiple root here, then we don't have any information or indication beforehand that there will be a multiple root. We can only speculate, okay? But there are, of course, we will draw upon such conclusions by which we may be able to see that we may be able to tell that there will be a multiple root. So one way to deal with the problem is that you take the function and take the derivative of the function. Remember that you take, if you have the function in the form of x, and if that function is differentiable, you take the derivative of that function at some initial value xi, and then of course for that x value of xi, the function, the derivative of the function should not be 0. If you take the function and its derivative, the ratio of that will be called as the if another function u. Okay, the ratio of this function to its derivative will be called as another function u, which will be also in x1. And uh, from algebra, we can easily say that the function, the new function which will be obtained in this way will has the roots at all the same locations as the original function. So in this case, if it is difficult to find the roots of function fx, it may be easier to find the roots of u of x. Okay, so we can use this type of observation to find the roots of the function, because the roots of both the u of x and f of x will be the same. So in that case, then you can, in that case, then we can substitute this relationship in this into the method of Newton-Raphson. So then we can find xi plus 1, and then we can find the xi is xi plus 1, that will be equal to x minus u xi plus u prime of xi. Okay, and then finally, okay, just look at the final formula. If we substitute this equation into the standard Newton-Raphson method, and then we do some simplifications, we also need to find the u prime of x as well. Then we can come up to this. We can derive this formula. Okay, xi plus 1 will be equal to xi minus f of xi into the derivative of that xi divided by the square of the derivative minus the f of xi times the f double prime of xi. Okay, that is the second derivative of xi. So in this case, we get a formula in which we also need to find the second derivative of the original function. In addition to the first derivative, we also need to find the second derivative of the original function. Okay, so let's apply this formula and modified Newton-Raphson method for the multiple roots. So use both the standard and modified Newton-Raphson method to evaluate the multiple roots of equation 6.11 with an initial guess of x naught is equal to 0. So what is equation 6.11? Yeah, equation 6.11 was this, okay? In the form of this x minus 3, x minus 1, x minus 1. Of course, you can very easily say that the roots of this equation are 1 and 3, because 1 is a double root, because x minus 1 is a factor which comes 2 times into this. However, of course, this is just for the illustration. This example is just for the illustration purpose to show you the methodology. So later on, this knowledge will help us to determine the multiple roots. So in any case, usually we will have the function in this form, x cubed minus 5x squared plus 7x minus 3. And normally when we have the function in this form, we normally cannot factorize that function, okay? So equation 6.11 is this, okay? And then now we want to apply the modified Newton-Raphson method. So for that modified Newton-Raphson method, we need the f prime of x. And also we need f double prime of x as well, okay? So by the standard method, we have this equation. By the standard method, we have this equation, xi minus f of x divided by f prime of x. So if we apply the standard method in this case, and then this equation, the Newton-Raphson equation, will be like this. Okay, so xi, and this is the f of x over here in the numerator, and this is the f prime of x in the denominator. And then we can solve it iteratively. So suppose we take the value of x starting from 0, and then we can get these results. Okay. So these are the results which we get from the standard Newton-Raphson method. From the modified Newton-Raphson method, we need to apply this formula. In addition to the first derivative, we need to apply take into consideration the second derivative as well. So second derivative will be 6x minus 1, okay, for this equation. So the second derivative equation will be like this, and then this should be also solved iteratively. So by iteratively, we can solve it like in this way. So in this case, in the standard result, we get this value of xi 0.977 after 6 iterations. But in the modified result, we get this rather quite close value of 1.002 after only third iteration. So you can see that the modified iteration method in this case is much faster.
Could you show again the modified version one?
Yes, so this is the modified iteration method equation.
Okay.
So let's see it because actually, well, it is already shown in the textbook. So what I do normally is that I try to evaluate these in Excel, okay? So for example, I have this equation, okay? So now I want to apply the Newton-Raphson method. Can you see the Excel? Can you see the
actually, we cannot see it.
You cannot see the Excel on screen? Oh, okay. Maybe let me change it. Yeah. stop the share and stop the screen one. So now can you see the Excel?
Yes. Yes.
Is it big enough?
Yeah, it's big enough.
Enough.
Okay. So suppose if I want to do this example on Excel by the user Newton-Raphson method. So how I will do it? So I will first take xi, okay, and then xi will be 0, okay, and then I will take the, and then that means that is the our, and that is my initial guess, okay, and then I will take the function of xi, that is, so that function we will evaluate using Excel. So is equal to x cube minus 5 times x square plus 7 times x minus 3. Okay, maybe I make it a little bit bigger. Okay. So then for the Newton-Raphson method, I need the first derivative. So f prime of xi. Okay, but what is x prime of xi? X prime of xi will be the derivative of this. So f prime of xi I can copy from here. F prime of xi is this. 3x square minus 10x plus 7. Okay, so it will be maybe just I put for my, yeah. So this is 3. Yes, maybe I can grow this. Yeah, so now 3x square minus 10x. So this is f prime of xi. So it is equal to 3 times x square minus 10 times x and plus 7. So this is the Newton-Raphson method, NR method. Okay, now in the Newton-Raphson method, I can apply, find the xi plus 1. Okay, the next iteration method. So the formula for the Newton-Raphson method is, this is the formula. Okay, so this is the formula for the Newton-Raphson method. So I just apply this formula. So it will be xi, so equal xi minus f of xi is this, divided by f prime of x is this. So now I found the value of x of I. So for the next iteration, I will use this value, okay, and then I will just copy it over here, and then I can now make some more iterations. So I have done the 6 iterations over here, okay, or maybe even one more. Okay, so this is the first, second, third, fourth, fifth. And what is the true error? True error will, because for this we know that the true solution was 1. Okay, so the true error will be 1 minus the estimated value. So it will be 1 minus, sorry, 1 minus the estimated value divided by 1 and times 100. So this is the percent true error. So the percent true error, you can see that from 100, 57, 31, 16, 8, 4, 2. And finally, I will get this value 0.9776 at a percentage error of 2.23, which is the same result which is shown in your PowerPoint. in your slides. So this is how you apply the Newton-Raphson method. Now, if we want to apply the modified Newton-Raphson method, we can also do that in Excel. Okay, so for the modified Newton-Raphson method, so modified Newton-Raphson method. Okay, so for this, what I can do is, because one more I need one more thing in this case. I need f double prime of xi. Okay, yeah, maybe I can take these values here. I need one more, f double prime of xi. Okay, so what is f double prime? F double prime is, so for example, f double prime will be 6x minus 10, right? Yeah, so it is, if you take the derivative of this, f double prime will be 6x minus 10, okay? So f double prime is equal to 6 times x minus 10. So this will be f double prime. So now I plus 1 will be, it is not, the formula is different. So this is the formula. So equal to xi minus, now f of xi is this, times f prime of xi is this, and then divided by f prime of xi square, and minus f of xi times f double prime of xi, and then this one. Okay, so I get this value. Okay, so in this case, what I have over here is, now for this next iteration, it will be the same value as this, and now I calculate it, and now in this case, because the value is coming as, yeah, we should always take the absolute value into the percentage error, so that other values are also plus. So in this case, maybe I take this. So what I can see is that this was the first iteration, second, third, and fourth. So I get, in the third iteration, I get a value of 1.002. And in the fourth iteration, the value is so close to the original value that the percentage true error is 3.73 into 10 to the power minus 9. But in this case, now you can see that this modified iterative method is producing us a very quick results. Okay, as you can see that.
I have a question.
Any question?
Yes. So, but what's the disadvantage of the modified version? Because I see that we use the second derivative, and is it always possible to find the second derivative?
Yeah, of course. If it is possible to find the first and second derivative and the first derivative, then this modified method can be used. So in this case, as we can see that by using the modified method, we get the solution is converging very rapidly. Okay? The solution is converging very rapidly. However, is this always the case? This I can show with the help of the example. Okay, so however, is it always the case? So this we can see by comparing the other root of this equation. So for example, as we know that 1 was the double root and 3 was the single root. Okay, so for this double root case, we can see that this modified Newton-Raphson method is producing the results rapidly. Okay, That means converges rapidly. But whether it also happens for the single root, so that we can also see it. So for the single root, the results have been compared over here. Okay, that means in this case, instead of starting from 0, because 0 was close to the double root 1. Okay, we start from 4. 4 is closer to the other root, which is 3. And here we can see that we get the single root in the standard method after 5th iteration, and the error is 2 into 10 to the power minus 7. But in the modified method, we also get the single root, but at slightly less accuracy, less accuracy, and you can see that the percentage error is slightly more. So in this case, you can see that for the case of the single root, there is no specific advantage for using the modified method. Okay. In the case of the double root, we have seen that the modified method is converging rather rapidly than the standard method. But in the but for the single root, the standard method is still better than the modified method. So we can reproduce these results on Excel as follows. Okay.
What if our, let's say, the slope on one of the slope of the function will be like not as steep, but it will be no, it will be steep, not rapid, but very slowly converging one. Will it affect our results very drastically?
If the slope of the curve is flat, then the convergence will be slow. But if the slope is steep, then the convergence will be fast.
So the both formulas will be effective, yes?
Yes.
The both Newton formulas. Okay.
Yes. Okay, so if I see, yeah, Excel. Excel is here. Can you see the Excel now?
Yes.
Okay. So if I apply this method, say for x is equal for the single root, okay, for finding the single root, then I will start from 0. For the multiple root, I started from 0. For the single root, I will start from 4. Okay, that means some other value. So in this case, now the values are changing. In this case, I need to change this term over here because the true root is 3 in this case. So I have to take 3 over here, and then need to take the absolute value. Okay, so it is 33.3, and now here I can see. So here I can see now this was the first iteration, second, third, fourth, fifth. Okay, so yeah, in this here we have done the 5th iteration. So it is 2 into 10 to the power minus 7, and the standard root is 3. So once we have already set up in the Excel, it is now easier to find it. For the modified method, maybe I can just copy and paste the data over here. Okay, and then I try from number 4. And now here I can see that, yeah, I need to change this formula. This is 3, and then 3, and then I will copy it down. So this was 1, 2, 3, 4, 5, 5th iteration. So let's apply the 5th iteration as well. So 5th iteration. So we get 2.99998, and then the error is 7.73 into 10 to the power minus 5. The error is 1.86 into 10 to the power minus 7. The same values which we obtained, 7.7, okay, 10 to the power minus 5. So therefore, you can see that actually I find it very useful to redo these examples using Excel. It gives you more confidence into your calculation. And then also once you set up the Excel sheet, it's very quick to perform the calculations rather than just look at the solution from the book or do by the manual calculator. Of course, in the exams you have to do with the manually on the calculators, but here with the Excel you can perform it rather quickly. Okay, so our conclusion by this example 6.10 is that for the multiple root, the modified Newton-Raphson method is better. For the single root, standard Newton-Raphson method is better. So provided that of course, the derivative first and second, first derivative is existing to apply in the second standard method, and also the second derivative is existing to apply in the modified method. So this is the conclusion. So do you have any question? Okay, so this was the case of the multiple roots. Remember that in the book there is another method which is the Brent's method. I have skipped that Brent's method in this chapter because it needs some more background, and that maybe we may cover later on in this course. Okay. So the Brent method is basically for the application of both approaches, the bracketing as well as the open approaches to find the solution. But in fact, I have skipped it from this chapter. So we may see it later on in this course. Okay, maybe in some other chapters. Okay, so now the last topic for this chapter is the systems of non-linear equations. So by the system of non-linear equation, we mean that we not only solve just one equation, but we solve two equations simultaneously. So as the example, you can see that you have these two equations, x square plus xy is equal to 10, and y plus 3xy square is equal to 57. So these two equations are non-linear because you can see that you have this x square and the power x and y are being multiplied with each other in this case. So these two equations are linear, and these equations these equations are in terms of the two variables. Okay, two equations in two variables, or you can see that if for example, if you take first equation and describe it as a function u, so that function will be will have two variables. Okay, that will not be a single variable function. So multivariable functions and the or multivariable functions and the, more than one equations have to be solved. So by the solution, what we will mean in this case is that we will by the solution, what we will mean is that over here is that we will take the by the solution, we will mean that we will find the values of x and y in such a way that both of the equations will satisfy. So this first equation and the second equation. So just as we do in the simultaneous linear equations, so we can also find the solutions. However, in the and as we can see in the simultaneous linear equations, we have some analytical methods. We can find these solutions, exact solutions, analytical solutions. But here, unfortunately, we don't have the analytical solutions. So we need to find their numerical solutions. So one of the simplest of the approaches to find the analytical solution is that you can write the equations in these forms. So u xy and v xy. Okay, in this form we can write the equations, and then we can use the Taylor series expansion of a function of more than one variable to find the solution of these equations. Okay, so we have looked at the Taylor series expansion in chapter number 2. Taylor series expansion can also be applied for more than one variables, not only for one variable, but 2 or 3 or even more variables. So this is the form of the Taylor series expansion for the function for more than one variable. So you can apply, you can represent these u functions in the form of the Taylor series. So u and v. So if you take the first equation as a function of u, as a function u, and if you take the second equation as a function v, so by the Taylor series expansion, we can look at these, the expansion of these equations. I will not go into the details of this Taylor series expansion. It is very similar to the concept which is in the chapter number, which was in the topic lesson number 3 or topic number 3 of this course. So finally, then maybe we can come up with the solution, okay, in this form, okay, solution of this in this form. So it will be better to see this solution, um, with the help of the example, okay? Then it will be easier to understand. So use the fixed point iteration method to determine the roots of equation 6.19 so that the correct pair of roots is x is equal to 2 and y is equal to 3. Initiate the computation with the guesses of 1.5 and 3.5. So we have these two equations. Okay, so suppose we have these two equations and we want to find their solution. Okay, although we know that their true solutions are 2 and 3, but suppose numerically we want to find their solution. So we can solve these equations like this. So in the fixed point iteration method. So for example, what we can do is we can take these two terms, that is x square and 10 on the other side, and then divide that by y. So we get x is equal to 10 minus x square over y. Okay. Similarly, for the second equation, we can write it like this. So we can take y and 57 on the other side. So it will be 57 minus 3xy square divided by, yes. So it will be, so we can, in terms of y, we can say that, yeah, in terms of y, yeah. So first equation we write in terms of x. X is equal to this, and then second equation we write y is equal to this. So this y, we keep y on this side and take 3xy square and 57 on the other side. So it will be 57 minus 3xy1 square. And now we remember that because fixed point iteration method we used like 1 week before. In the fixed point iteration method, we use these kinds of equations iteratively. and then we can find its values. So for example, first we take the our initial guess of 1.5. So we will put the 1.5 value over here and then 3.5 over here, and then this will give us our guess for the value of x. Okay, this guess for the value of x we can use into this equation. Okay, and then the value of y was previously as it was used over here, and then it will give us the value of y. And in this way we can iteratively solve it. So for the first guess of x will give us a value of 2.21. So we can see that from 1.5 we have moved to 2.21. Okay, and then for the value of y, if we input in this value of y from the value of x, the previous value of x, we get the value of y is equal to minus 24.375. So from a value of 3.5, we are moving to minus 24.375. So in this case, we can see that the solution is kind of diverging in this situation. If we take one more, if we take one more iteration, so the value of x will be minus 2.209. And the value of y will be even worse, 4.429. So in this case, you can see that the solution is diverging. So it means that we cannot continue like this. So we have to do some other way. So what is the other way? The other way is maybe that we can write the equation into this form, okay? And then apply the method and write the other equation into this form. So the same equations we can write in different forms, and then we apply the values. So first we apply the 1.5 and 3.5, these two values. So we get this value, and the value of y we get is 2.86 in this case. And in the next iteration, we get the value of 1.94, and then we get the value of 3.04. So in this case, we can see that the solution is kind of not diverging, and it may converge to the true values of x is equal to 2 and y is equal to 3. So this was the approach for the solution of the simultaneous equation, simultaneous nonlinear equations by using the by using the fixed point iteration method. So let's see it with the help of Excel. Okay, how we can do it in Excel. Okay, so maybe, yeah, this was the equation which I wanted to use. So and then let me apply this, input these values over into Excel over here. Okay, so we have to use these equations and here, so that we can immediately see it. And here, so can you see the Excel?
Yes.
Yes.
Okay, so now I am applying the fixed point iteration method. Fixed point iteration method. So what is the fixed point iteration method? In this case, I will take the xi, okay, and I will start from x is equal to 1.5. Okay, yeah, I will start equal to 1.5, and then I will calculate the next value of x. So because from x is equal to 1.5, and then yi will be equal to yi as the starting value I'm taking equal to 3.5. Okay, so this is what was done over here. Yeah, x is equal to 1.5, y is equal to, so starting values are 3.5. So now what we get is now what I get is, so the next value of x I will get from this 10 minus x over yi. So is equal to 10 minus x square divided by yi is here. So this is the modified value of xi. So what will be the value of yi? Yi will be 57 minus 3xy squared. So it will be equal to 57 minus 3 times x. So in this case now I will use the updated value of x, not this previous value of x. So updated value of x I will use times the last available value of y is this one. Okay, so this will be the I need to take the square from here. So in this case, I get the minus 24.375. So the same results as as I have seen in the minus 24 and 2.24. And then now it is easy for me to perform the next iteration. I will just drag it, okay? And then I can perform as many iterations as I like. So in this case, I can see that the the values are not converging towards this real solution. So you can see that the value of y is increasing. So diverging, okay, diverging case. So therefore, this form of the equations will not apply. And let's see for the how we can converge it. So in this case, we can apply this form of equations like this. We need to try it, okay? So for example, over here, and the other is here. Okay, so you can see that from this original equation, we can write this equation in this form. Do you agree? So from x squared plus xy minus 10 is equal to 0, we can write it like this. And then from the second equation, we can write it like this, okay? So you agree with that. So now if we apply this approach into the fixed point method, so what we can do is that we can say xi and yi. So as before, we take 1.5 and 3.5, okay, and these two values. Now I calculate the new x value of x. So that is equal to square root I will use the sqrt function of xl, square root 10 minus xy. So that is x is this, and times y is this value, okay. And now 2.17494 I get. For the y, I will take sqrt square root function of what? 57 minus y is this, and then divided by 3 times x. The value of x will be the latest value, not the previous value, okay. So this, and then close it, and then I will take. So it will be 2.86. So 2.17 and 2.86. These were the same values which I got it before, okay. And now I can easily expand it, okay, and then just drag it down, and then I can see that now the solution is converging. In this case, 1.99 and 3, because 2 and 3 were the 2 and 3, yes, 2 and 3 were their original solutions, okay. 2 and 3 were the original solutions. So for example, if I put 2 square is 4, and then 4 plus 6 is 10, 10 minus 10 is 0. Yeah, 2 and 3 were the original solution. So in this case, you can see that the solution is converging. So what we have learned from this method is that the fixed point iteration method sometimes may not converge, but by changing some different form of the equation, we may get the convergence. We may get the convergence. However, theoretically, it has been found that In order for this method to work very well, our initial guess should be closer to the real values. So for example, in this case, the real values were 2 and 3. If instead our initial guesses were much away from these two values, then by any type of form of this equation, okay, we may not be able to find the solution. We may not be able to converge on the solution. So in this case, the main point over here is that our initial guesses should be closer to the uh, uh, true value. However, this type of condition is very restrictive and it is very difficult to achieve for many types of equations. But this type of restriction or this type of condition is very useful for the linear, for the numerical solutions of the linear simultaneous equations. That, of course, we will see in later on in this chapter. So the best way to do to apply such method is to try to use the trial and error method to first get a closer approximation of the results, and then apply this fixed point method to get the more accurate approximate results. Okay, so this was the solution of the simultaneous equations by the fixed point iteration method. There is another method which is left as the modified Newton-Raphson method for the solution of the nonlinear simultaneous equations. So this method also uses one example, but let's leave it for our next lecture. So in the next lecture we will complete this topic, one example left, and then we will start the next topic as well. Okay, so do you have any questions?